Have you ever watched one of those crime scene shows like CSI or CSI Miami or even CSI New York? In all of those shows, you see episodes where police officers are working with forensic chemists to try to solve a crime. In how many of those episodes that you've seen is there a mysterious white powder found at the scene of the crime, and they have to determine what is this mysterious chemical? What if you were the forensic chemist and it was your job to analyze the sample and determine what the chemical is? What information do you think you would want to know? It would probably be a good idea if you could find out what elements are found in this compound. And then let's think about what a chemical formula actually is. A chemical formula tells you how many atoms of each element are in the compound. For instance, when we talk about plain old water, we know that the formula has a 2 for the hydrogen, and we know that there's a 1 for the oxygen. Sometimes chemists are lazy and we don't actually write 1s in, but we know that there's a subscript of a 1 right there. This tells us that there's a ratio of atoms in this compound. It's always 2 hydrogens to 1 oxygen atom. This ratio is very important because it tells us about the identity of the substance. So if you were trying to figure out what is this mysterious white chemical, not only would you need to know what elements are in this compound, you'd also need to know that very specific ratio of atoms in the compound. If you're a forensic chemist, you tend to work with a lot of different things. You need to be able to analyze hair samples, blood samples, sometimes shattered glass, and even paint fragments. To do all those things, you need a little bit of background in all these different areas, such as chemistry, biology, a little bit of genetics to know about DNA, and even a little bit of materials science. Let's say we analyze this white powder, and we were able to figure out that it contains carbon, hydrogen, and oxygen. What would your next step be? How would you figure out that distinctive ratio of atoms in the compound? In order to learn a little bit more about this chemical, we would need to figure out how many carbon atoms are there compared to how many hydrogen atoms are there versus how many oxygen atoms there are in the compound. We're about to do a little bit of math to help us figure out this basic formula. All right, so after analyzing the compound, we're able to find out some important information. We're able to figure out how many grams of carbon, grams of hydrogen, and grams of oxygen there are in the compound. And you can see those masses written on the board. Now we need to be able to compare the number of atoms of carbon to the atoms of hydrogen to the atoms of oxygen. Do you think that we can simply compare the grams of each? Would there be any problem with doing that? You got it. Carbon atoms and hydrogen atoms and oxygen atoms are not the same size. Hydrogen atoms are so teeny tiny. Carbon atoms are about 12 times bigger, and an oxygen atom is 16 times bigger than a hydrogen atom. So if we're trying to compare atoms of this to atoms of that, you can never compare grams of elements. The only thing you can do is compare moles of elements, and here's why. Remember what the word mole means. A mole represents a huge, huge number of atoms, a number that's so big we can barely comprehend what it even means. But we know that when we have 1 mole of a certain element, we always have the same number of atoms in that pile. So if we could convert our grams to moles and compare our moles to each other, then we would have a really good way of comparing the number of atoms of each. So let's do that. Do you remember how to convert grams of an element to moles of an element? we're going to need to look at a periodic table and determine what the molar mass of each of these elements would be. Why don't you grab your periodic table and do that calculation along with me. Take a look at my molar masses and see if they look just like yours. For carbon, I said that 1 mole of carbon would weigh 12.01 grams. A mole of hydrogen, since hydrogen atoms are so much smaller, weighs only 1.01 grams. Oxygen, if I had a mole of it, would weigh 16.00 grams. Now we're able to take our grams of each element and convert to moles of each element. Go ahead and do those calculations now. Check your numbers. Do your calculations look like mine? I now have my moles of carbon, my moles of hydrogen, and my moles of oxygen. We can now compare our moles of each and decide what's that ratio of carbon atoms to hydrogen atoms to oxygen atoms simply by comparing their moles. How do you compare numbers to each other? What's the best way to do that? Well, a great way to compare two numbers is to take the big number and divide by the small number. As I look at my different numbers of moles of each element, I can see that one of them is smaller than the other two. As you take a look at the oxygen moles, I'm hoping you can tell that it's smaller than the carbon and the hydrogen. So to compare these different numbers, we're going to take each value and divide by the smallest one. We're going to take each one and divide by 0.0174 moles. So you'll notice what I did. I took each of the values and divided by 0.0174 moles, and I only did that because the moles of oxygen were the smallest number of moles. Now what I'm hoping I'm going to find is a whole number ratio of carbons to hydrogens to oxygens. Let's find out if that's what happened. Let's check it out. When I compared my moles of each element to the smallest number of moles, here's what I found. For carbon, I got a value of 2.25. For the hydrogen, I did get a whole number, and it was 2. And for the oxygen, of course, when I compared it to itself, I got a value of 1. Well, what we were hoping for when we compared the moles to each other was actually perfect whole numbers. Because if they had been whole numbers, those would have been the subscripts in the formula. You see, a mole ratio, a mole comparison, actually gives us an atom comparison. How many atoms of this to how many atoms of that are in the formula? The oxygen would be 1. The hydrogen would be 2. But uh-oh, there's a problem. When I look at my carbon, I get 2.25. How can you have 2.25 atoms of an element? That's not going to work. Here's what we can do. If we could multiply all 3 of them by a certain number that would make them turn into whole numbers, that would give us the subscripts in the formula. So think about it. What could I multiply 2.25 by in order to get that to be a whole number? You're right. I could multiply it by the number 4. And if I multiply it by the number 4, this will turn into a 9. Our hydrogen atoms now become 8. And our oxygen atoms become 4. Do you realize that we just figured out the formula for this compound? Now we know the subscripts for this unknown, mysterious white chemical. We've learned quite a bit of information about it. This is really exciting because we were able to take experimental data and figure out the formula of this compound. I do a little research and I look up C9H8O4. And guess what? It's aspirin. So chemical that the police officers found in the bag that we were really worried about? It's simply aspirin, which we use for reducing fevers and for easing aches and pains. Problem solved, right? Well, not so much. One last thing that we want to do as an analytical chemist or a forensic chemist is use a fancy instrument called a mass spectrometer. A mass spectrometer gives us the molar mass of the compound that we're analyzing. So let's say we analyze our compound in the white bag and we find the molar mass. We find that the molar mass of the compound is 360.32 grams per mole. Sounds great, right? There's a problem. If you look at the formula, I know that you could easily calculate the molar mass of this compound. Let's add up all the individual molar masses and find out what was the molar mass of this. As it turns out, the molar mass of aspirin is 180.16 grams per mole. They don't match up. What did we do wrong? We actually didn't do anything wrong. The process that we went through where we took our grams and we converted them to moles and then compared our moles to get a ratio of atoms for the formula was really a great idea. But what it gives you is something called an empirical formula. An empirical formula is the lowest possible ratio of atoms. In other words, whatever those subscripts really are, when you reduce it down, you get a ratio of C9H8O4. The empirical formula is not always the true formula. The true formula is actually called the molecular formula. And oftentimes, it's a multiple of the empirical. In other words, maybe all of the subscripts are multiplied by 3, or maybe they're all multiplied by 5. How am I supposed to figure out what the molecular formula is with the information I now have? Well, we really have some great stuff here. We know the true molar mass of the molecular formula, 360.32 grams per mole. And we know what the molar mass of the empirical formula is. It's 180.16 grams per mole. Do you notice anything about them? Do you notice that this number is roughly twice as large as that number? Let's do a little bit of math just to check that out. Take a look at our math. We took the molar mass of the molecular formula. This is the one in the numerator. We divided by the molar mass of the empirical formula. And we know the empirical formula is the formula with the lowest possible ratio of atoms in it. When I compare the two, notice that the molecular formula is twice as large as the empirical formula. So how do we write out the molecular formula? If it's twice as big based on the math, we're going to take all the subscripts in the formula and multiply each one by 2. So C9 becomes C18. And H8 becomes H16, and O4 becomes O8. This is what we call the molecular formula, and it's often a multiple of the empirical formula. So what is this chemical? If this was aspirin, this is not aspirin. This is something completely different because it's got a different number of carbons and hydrogen, oxygens all put together. A little bit of research would tell you that this is rosmarinic acid. It is an antioxidant, which is actually found in many herbs such as oregano, thyme, and rosemary. I hope you found our lesson on forensic chemistry, empirical and molecular formulas useful today. We're now going to do some practice and do some examples together to make sure you've really got it. In this part of our tutorial, we'll be practicing some empirical formula problems. Make sure you have a periodic table ready, as well as a calculator and something to write on. Let's begin our first practice problem. Here's the situation. A chemist determines that a substance contains two different elements, 3.79 grams of carbon and 0.32 grams of hydrogen. And what we want to know is, what is the empirical formula of this compound? Let's recall how to do a problem like this. If you're given grams of different elements, remember, you can never compare grams of elements to each other. And that's because the atoms of carbon and hydrogen are different sizes. So comparing the grams of each will not give us a ratio of atoms, which is what we're looking for to find the subscripts in the formula. So the first thing that we want to do is take our grams of each element, and we're going to convert those to moles. So we're going to take 3.79 grams of carbon, and remember the conversion factor. To go from grams to moles, you need to find the molar mass of carbon on your periodic table. And your calculation should look a little bit like this. Let's do the same thing for our grams of hydrogen. When we look up the molar mass of hydrogen, it's 1.01 grams per mole. Doing a little bit of math helps us convert to moles. 0.316 moles of carbon and 0.317 moles of hydrogen. It's interesting that those moles are nearly the same number. Let's compare our moles of carbon to our moles of hydrogen. We know they're very similar to each other, but can we quantitatively compare them? The best way to do that is to divide by the smaller of the two values. Our moles of carbon look like they're just a little bit smaller than our moles of hydrogen. So let's divide each of those values by 0.316 moles. When we do that, we get one carbon atom to every one hydrogen atom. In other words, our moles of carbon and our moles of hydrogen are the same. This is important because that ratio of atoms is what we're looking for. Those are going to be the subscripts in our formula. So when we first started off, we were trying to figure out what is the subscript that goes with the carbon and what's the subscript that goes with the hydrogen. We now know that the atoms of carbon and the atoms of hydrogen are the same in that formula. One way to write that would be C1H1. But don't forget what I always say. Chemists are lazy. We tend to ignore the ones and we simply don't write them, but we certainly know that they're there. So what we tend to do is write the formula as plain old CH. So this is going to be our empirical formula. The lowest ratio of atoms is 1 to 1. Now that we've figured out the empirical formula, let's try to find the molecular formula. Recall what this is. If the empirical formula gives us the lowest ratio of atoms in the formula, the molecular formula is the true formula. And typically it's a multiple of the empirical. Maybe it's 5 times larger, or 2 times larger, or 7 times larger. To find out the molecular formula, we need one more piece of information. We need to know what is the molar mass of the real compound, of the true formula. You could use an instrument like a mass spectrometer to help you determine what that molar mass is. So let's say an analytical chemist helps us find out that the molar mass is actually 78.11 grams per mole. What I'd like to do is compare that molar mass to the empirical formula that we determined a few minutes ago. The empirical formula was CH, 1 carbon and 1 hydrogen. Do a little calculation with me. Let's find out what the molar mass of CH is. Again, looking on our periodic table, we know that a carbon has a molar mass of 12.01 grams per mole, and a hydrogen has a molar mass of 1.01 grams per mole. When we add that up, it's 13.02 grams per mole. Now let's do something really cool. Let's compare the molar mass of the molecular formula to the molar mass of the empirical formula. The molar mass of the molecular was 78.11. In the little calculation we just did, we found out that the empirical formula had a molar mass of 13.02 grams per mole. If the molecular formula is a multiple of the empirical formula, when we compare their molar masses, we should find out what that multiple is. When we compare the molar masses of the molecular formula to the empirical formula, we find out that the molecular formula is 6 times bigger than the empirical. This is great information. We know that the molecular formula is a multiple, and in this case, it's 6 times larger. Here's what we do with that information. We take our empirical formula, which is CH, and we multiply every single subscript by the value 6. Since we had C1H1, our molecular formula must be C6H6. Are you ready for problem number 2? This time we're going to be talking about the chemical NutraSweet. NutraSweet is also called aspartame. It's an artificial sweetener that's used instead of sugar. You'll notice that we're given something a little bit different in terms of our element breakdown. We're given percent composition. We know that 57.14% of the mass comes from carbon, 6.16% comes from hydrogen, 9.52% from nitrogen, and 27.18% from oxygen. Using those percent compositions, we'd like to find the empirical formula of NutraSweet. In the past problem, we were given grams of each element. Let's come up with a way to figure out how do you work with percent composition. Here's a trick that's really easy to do. Let's assume that we have a 100 gram mass of the NutraSweet. If that was the case, then 57.14 grams would be coming from the carbon, 6.16 grams would come from hydrogen, 9.52 grams would come from the nitrogen atoms, and 27.18 grams would come from the oxygen. This is a really easy way to deal with percent composition. The percents simply turn into the grams. You know what to do next. We're going to take those grams, and since we can't compare grams, we have to turn them into moles. Let's find some molar masses and calculate how many moles we have of each element. For carbon, the molar mass is 12.01 grams per mole. For hydrogen, 1.01 grams per mole. Nitrogen, 14.01, and oxygen, 16.00. When we calculate, we can see the moles of each element that we have. Remember the next step? We've got to compare all of these values. The best way to compare the number of moles is to look for the smallest value. Take a look at all 4 of the values. Can you see that the moles of nitrogen are the smallest out of the 4? In order to compare the moles, the best strategy is to take all the different numbers of moles and divide by that smallest value, which we said was 0.68 moles. Now, that will give us a comparison of the atoms in the formula. When we do this comparison, we find out that the formula should have 7 carbon atoms in it, 9 hydrogen atoms in it, 1 nitrogen atom in it, and 2.5 atoms of oxygen. If we were to write the formula, look at how crazy that number for oxygen looks. 2.5 atoms. Who ever heard of something as silly as that? That's not going to work. When we find the subscripts, they're supposed to be whole numbers. Let's think of a simple way that we could deal with this problem. Is there a number that we could multiply that 2.5 by to get a whole number? That's right. We could multiply 2.5 times 2, and that would give us 5 atoms of oxygen. But whatever you do to one of these numbers, you have to do to all of the values. So we're going to take the values that we see in blue, and we're going to multiply each one by 2. So that gives us 14 carbon atoms, 18 hydrogens, 2 nitrogens, and 5 oxygens. Our numbers now become the subscripts in the formula. NutraSweet would have an empirical formula of C14H18N2O5. Great job, guys! This concludes our tutorial on empirical formulas. I hope it was really helpful. Thanks for joining us today.